So let's go ahead and solve the Nernst equation for each of the two half cells. Now, let's also go through it in the order that we would do this if we are then going to calculate the whole cell potential. In other words, start out with your right-hand side, and then we'll do our left-hand side. So go ahead, pause the video, and try the cathodic side right now, and then hit play. We'll hear that part. We'll pause again, and we'll try the anode side. Okay, so since we have these values for our cathode, let's go ahead and work that one out. We look at it and we say, we need to know E naught. So hopefully you have your equations booklet handy digitally. If you were stuck and you didn't do that, go ahead and pause now, open that, find it, and then continue. Okay, now assuming that you did have, we come over to your equations booklet. Now, if you didn't have your booklet and you want to give it a try, now that it's on your screen, please do, because this is definitely something to get some practice with. So we're in the silver section. You'll notice here what we need to do is find the half cell reaction that's appropriate for what we're talking about. Now, the key part that we're focused on is that we had an Ag plus and an electron giving us silver solid. We don't want to go from +3 to +1 or +2 to +1 or anything like that. We want something that goes from +1 over here to neutral, our silver solid. But also notice, we don't have any of these specific reaction conditions around, so we don't want to focus on any of those. Those are actually something a little bit more complicated, just here so that you have access to them quickly. This is the piece that we care about, and so we have our E naught as 0.7993. So 0.7993 minus 0.05916 over how many electrons were being passed. Well, for our balanced half reaction, we don't have to worry about this keeping it in the 2, 2, and 2. We can just do this for 1 electron. Now if I put in that 1 electron, then when I get over to here, I'm going to say log of Q. I go to put in my Q. I say that my reactants are going to be silver ion. They go on the bottom. We specified that its concentration will be 0.50. We come up here to the top. The only product we have is a solid, which is going to have an activity of 1 at all times. And so we have that number there. Now I'll point out, you might have said, well, wait a minute. What if I just go ahead and plug in the 2? You keep saying that it's okay for us to use it even if it is multiplied. Prove it. Okay, well then let's go ahead and calculate it both ways. So we're going to need to grab a calculator in a second and get that piece. Let me do it the alternative way that we're saying should give us the same result. 7993 minus 0.05916 over 2. Then this will be log of 1 over, see my stoichiometry, it'll be the 0.50 squared down here now. Okay, so let's grab a calculator and do this. We'll start here at the end. So we have 1 divided by 0.5, which will be 2. We're going to take log of 2. So we've got that last term. Now we need to multiply it by this value. So times my, I'm going to do this with the keypad, 0.05916 divided by 1 equals this value. It's a negative number, so what I'm going to just do is I'm going to say negative value, there we are, and I'm going to say plus 0.7993. So my current voltage, my current potential for that should be 0.7815. Okay, so 0.7815. And let's get a unit on that. There we are. Now let's try it the other way, just to make sure that we really can get away with having either of those stoichiometry approaches. All right, so let me just clear that. So now it's going to be 1 divided by 0.50 squared. So let me just do the 0.5. I'm going to go ahead and square that. So 0.25. So 1 divided by 0.25, it's going to be 4. I take the log of 4. I get this value. Now let's go ahead and multiply that again by 0.05916 divided by 2. There's that same value we saw a moment ago. We're going to go ahead and put the negative sign back on that. We're going to add on my 0.7993, so plus 0.7993, and there's the exact same answer once again. So you can see that we get the same result either way. So don't let that spook you. Go ahead and just use your calculations. Now I'm going to go ahead and erase some things, and you can see that I've cleaned up the answer as well so that it's a little more legible. There. So we should have probably included our sig figs. Notice we had 2 sig figs in our concentration. So we probably have too many sig figs showing right here to trust. I'm going to go ahead and ignore sig figs for this problem though, just so that we see the example without too much goriness sitting on top. Alright, so now let's go ahead and do our calculation for the anodic side. In fact, let's emphasize what we've already got by putting it down here. Now we'll do the same thing for anode. Go ahead and give it a pause and give it a try. Alright, let's do it. So we have E equals, I need to go get my E naught. We come to the cadmium section of our booklet. We see that we have a couple of different equations we can be looking at. We know that we had a 2 plus becoming neutral. This one is when it's actually in mercury. And remember, you can have metals become amalgams when they're dissolved inside of mercury. And that can drastically change how much energy is needed to pull off electrons. So make sure you only use it if it actually is in mercury. We don't have mercury, so it must be the second one. We find E naught to be negative 0.402 for the way that it's written. So we're going to bring that back over. So minus 0.402 volts. Now, you might have said, wait a second, though, you reversed your reaction. That means we've changed our sign. That is one of the ways you can solve this problem. But we'll come back to that idea in a minute. What I'll do is, just as a reminder, I'll put plus 402 with a question mark right here. We're going to come back to this in a second. All right, so I've got that number. Let's go ahead and do my minus 0.05916. How many electrons were being passed? Well, we say that balanced chemical equation has 2 electrons. So it's going to be over 2. We do log of, same sort of thing as before. I haven't reversed my reaction, so I still have my, well, I haven't reversed my half cell potential, I should say. So I still have this as my reactant, and this is my product, the way that I've got it written. So I'm going to go ahead and put in my ion. I have CD2 plus concentration as 0.010 molar. My solid will be on top as 1. So again, let's grab the calculator. Okay, so we have 1 divided by 0.010 gives us 100. Now we're going to take log of 100. We're going to get 2. So it'll be 2 times 0.05916 divided by 2. That's going to be my last term. Now that's going to be a negative sign on there, so let's go ahead and hit the negative sign on that. Now we still have to apply this subtraction. See, it's a negative sign on that, so we'll do minus 0.402. So we're saying that this should be negative 0.461. Now, why didn't we go ahead and actually do it the way that we have it written, though? Well, here's the thing. The way that I want to treat us to handle this problem, use the reaction that you see in the handout. In other words, do it for this reaction that you see listed over here. Now that feels a little weird to say, well, don't actually put it the way that you see it in your equation. The reason is that when you come back over, the sign change is going to be handled depending on how we consider the left side and right side cells. We either are going to subtract them or we're going to add them. If you do reverse this reaction, you're going to end up getting the exact same value, just with an opposite charge. You're going to have a positive sign on that. And so what's going to happen is you're going to end up adding together your voltages, which is not what we saw in the previous video and in previous slide, but both these can be valid ways to handle the solution, as long as you're being self-consistent. So let's see it the way that I'm saying we should solve it, and then I'll show you the other way in a second. All right, so right now I said that this potential is going to be minus 0.461 volts. Our previous video said that we're going to then do E equals E right minus E left. So notice that that's going to be energy on the right hand side, so 0.7815 minus negative sign 0.461 volts. Now, since my mind isn't quite up to addition and subtraction right now, I rely on my good friend the calculator. I say 0.7815 plus 0.461 gives me 1.24 volts. And like I said, I'm being dirty about my sig figs right now, but I'm going to let that slide. So that's what I'm expecting to have as my potential difference. Now, this is what I get my way. What if we do it the other way that isn't being shown in our textbook and isn't being shown in our videos? What if we had reversed this reaction, or rather done this format of the reaction, and ended up with a plus 2.46? So let's go ahead and use a different ink just so we don't confuse these two things. So in that case, we would have ended up with positive 0.461 volts for reversed. Now the appropriate way to handle that is we're just going to add the two energies together, because we've already accounted for the sign change by changing the sign here. So now it turns into total energy equals energy of the right plus energy of the left. We add those together, you're going to get the exact same value. A positive number plus a positive number is going to give you 1.24 volts once again. So we get the same thing if we do the plus way. So pick one and stay consistent with it, and you'll be doing okay.